Hey there, how we doing? We're back to finish up our work on mathematical induction. We're up to problem 10, and we've got a few more of plain induction, then we move on into the strong induction proofs. So let's get right after it here. Problem 10 says prove that, and really what they're doing is like a dot product of two n vectors. One has the natural numbers 1 to n, the other has the factorial of the natural numbers up to n, and show that that dot product is n plus 1 factorial minus 1 for all natural numbers. So proof would look something like this. And by the way, if you've not attempted this on your own, you should do that before you're watching this. You know, what I want you to do is go through and check your work against this, but I do want you trying things on your own. And I'll always post these after we've had the chance to work them in class anyway. Okay, so first thing we're going to look at the n equals 1 case. So note that 1 times 1 factorial is 1 times 1, which is 1. And let's look at the formula. 1 plus 1 factorial minus 1, well, this is 2 factorial, which is 2. So 2 minus 1 is 1. So the initial step, or the basis step, holds. Okay? So now we want to do the inductive step. So we'll assume that this works for k, some natural number k. Now, assume that 1, 2, 3, k dotted with 1, 2. These are all factorials, factorial. K factorial is k plus 1 quantity factorial minus 1 for some natural number k. Alright? And that would be 1 greater, right? Then consider what happens when we do this up to k plus 1. Okay? Well, when we do that, and let me just write it here so I'll get it over to the side. What we can really do is look at the first k components of these two k plus 1 vectors, right? And, just realized I'm probably wearing a bad shirt for this. I got the whole moire thing going here, but it'll be alright. We can just take the first k components of these two k plus 1 vectors and dot product them. And then do the last two components ourselves. So this would be k plus 1 times k plus 1 factorial. Alright? Now, our assumption is that this first part is k plus 1 factorial minus 1. And then I've got this part, the plus k plus 1 factorial. Now, it's good to keep in mind, I always talk about kind of having the end in mind when we start this. What we're going to do is prove this for k plus 1, which means replacing this k with k plus 1 will give us k plus 2 factorial minus 1. So that's really our goal, is to get that if we can. An obvious thing to do here, you've got a k plus 1 factorial. Well, okay, let me say this first. The minus 1 we've already got, right? Here's the minus 1, so I'm probably going to leave that alone. I've got k plus 1 factorial in two of these terms, which I can factor out. So let me go ahead and do that. That would leave me with 1 here. I'm going to leave that minus 1 alone for a moment. And then here I would be left with k plus 1. And then the minus 1 I'm not doing the factoring deal with. So when I do this, I've got now, this is k plus 1, so this is k plus 2. This is working. So I've got k plus 1 factorial times the term, the factor right after that, k plus 2. So that is then k plus 2 factorial minus 1. Okay, and then we just throw in our closing sentences here. Thus, the inductive step holds. Therefore, the formula, holds for natural number n. Okay? Turns out that one wasn't too bad at all, was it? Alright, that is problem 10. Let's see if we can do, the next one is 11. We've got an A and a B on 11. They've got a formula here that they want us to prove, and A says use induction, B says use a direct proof. And then I think there's actually even a C says which is easier. Well, I don't, it doesn't matter, right? We're going to do them both anyway. So proving this for natural number n means it has to hold first for 1. Okay. So I would say something that, alright, note that with 1 we would just have this one term, 1 plus 1 over 1, which is 2. And then check the formula, 1 plus 1 is 2 as well. So the initial step holds. Now, assume that this works for some k that's a natural number that naturally makes it 1 or bigger. Okay. Consider, and now the one we want to take a look at is what happens when we take this on out to k plus 1. Well, this part of it is right there and back, right? So this part right here, we are making the assumption that this is k plus 1. Oops, let me put it right here. Times 1 plus 1 over k plus 1. So we can just actually distribute that through, right, and get k plus 1 times that, and then plus another 1. And our goal here would be to get k plus 2, correct? This formula with k plus 1 in it, which is what we got. So, kind of our closing sentences, thus, the inductive step holds. Therefore, by induction, the formula holds for natural number n. Okay? So that wasn't very hard. The direct proof of this, though, is actually possibly even simpler. if we're looking at 1 plus 1 over 1, 1 plus 1 over 2, and a dot, I'll go back one step just so you'll see 1 plus 1 over n minus 1, and then 1 plus 1 over n. Well, what you can do here is get a common denominator in each of these terms, right? So here we'd get 1 plus 1 over 1, that's simple enough. And here you get 2 plus 1 over 2. And here you get n minus 1 plus 1 over n minus 1. And here you get n plus 1 over n. So there's kind of a pattern to this, right? It's 1 over 1, 3 over 2. I'm sorry, 1 plus 1 is typically 2, okay, even on Sunday. And so you've got this pattern, right? And then you've got here n over n minus 1 and n plus 1 over n. Well, if you can see what's happening here, the numerators and denominators, there's something right here that would knock that out, and this one knocks that one out. And so all you're left with is n plus 1 over 1, which is n plus 1. And you're done. Box, box. Okay? So it's really not hard to prove directly in that case. Which one's easier? I don't know. This one took less ink, but I don't know. Good news is that we can work it both ways, right? All right, so 12 is when we start to get into the strong induction proofs. A strong induction is when you have to go back and look at more than just the previous thing. Okay, we've been assuming it holds for some k and then showing for k plus 1. But in many cases, we'll need to look farther back than that. So what we have to do in those cases is we have to go back and say, if there is some minimum number that we have to go back and look at, then we have to do more than just one little basis step. I mean, we'd have to look at the first couple things, okay? In this one, because we're going to go back 1, yes, but we're going to go back 2, so we need to do the first 2 initial steps. That way, when we start talking about k is going to be the last one that we do. The last one that we do, and then we have to be, when we go to k plus 1, we've got to be able to look back 2. Okay. So here's the way we start these kind of proofs. And what we're trying to prove, by the way, we've got a sub 0 is 0, a sub 1 is 1, and a sub n is defined like this for n 2 or bigger. We want to show that a sub n can be, this is called a recursive definition of a sub n, because it goes back and looks at previous values. What we want to show is that there's a closed form way of representing a sub n, and that is n squared. Okay. And actually, they don't give you that. They have you play around with it a little bit by doing 2, 3, 4, 5, and so forth. But every time you're getting a perfect square, it's not hard to kind of see that. So what we do is kind of show that this works for the first couple. Now, the first couple, because we got to look at least 2 back here. Okay, not at least. We always have to look 2 back. So note that A0 is 0, and that 0 squared is 0, and also A1 is 1, and 1 squared is 1. Okay. Thus, the initial step holds. Now, I want you to pay careful attention to this, because this is really the difference between regular induction and strong induction. Now, assume that a sub k is equal to k squared for, and I typically do this with j. That's right, I'm sorry, I'm getting ahead of myself. How about I just start over on that line? Okay, sorry. I'm thinking one thing, and yet I'm trying to be consistent with what how I've been writing. So okay, now assume that a sub j, I typically use j for this, is equal to j squared for integer j, went from 0 up until k, for some integer k, and we always go with the last one that we proved here, the 1. Okay, so it can be much bigger than that, but at the very smallest, it would be 1. The reason is that when we go look at k plus 2, okay, that's 2. We've got the 2 previous things that we can look at. Does that make sense? Okay, I don't know why I'm asking. You can't answer me, but hopefully that makes sense to you. That we have to at least get far enough out there to where if we apply our rule, you know, we've got enough reach back values. Okay? Consider a of k plus 1. Okay? Now, by formula, this would be 2a, and then I subtract 1 from this number, so that's k, minus a, and now I subtract 2 from this number, so that's k minus 1, plus 2. Okay? Now, for k and smaller, we have said that, okay, in those cases, these are perfect squares. All right? So this is 2k squared. That's applying our assumption. Minus, and now this is k minus 1 squared, quantity squared, plus 2. Now what I'd like to have happen on this is I hope that this ends up being k plus 1 quantity squared. Right? So let's see what happens here. We got 2k squared, that's good, minus, and now let me put all this in here, minus 2k plus 1, in parentheses still, plus 2. So that's, let's subtract these now. This is going to be just 1k squared. And then minus a negative 2k, so that's plus 2k. Oh yeah, baby, this is looking good. And then minus 1 plus 2 is plus 1. And that is a perfect square. That's k plus 1 quantity squared. Okay? Thus, here's our closing sentences. The inductive step works. Therefore, by strong induction, a sub n is n squared for integer n greater than or equal to 0. Okay, box. All right. So trying to make sure that you see the usefulness of this type, this variation of induction, and then see that you're making the correct kind of assumptions here. Make sure you got your bounds on J right, your bounds on K right, and all those kind of things. Okay. All right. 13. Again, it's going to be a case where we need to use strong induction. It says, in a basketball game with no fouls, which would probably be a really rare game, players may score 2-point and 3-point goals, prove that any number 2 or greater may be scored. Okay. Well, the idea on this is that once we get to a certain point, we want to just say, oh, well, if you can get the previous ones, just add 2 points to it, right? So, just talking this out with you now, it seems pretty clear we can get a 2-point score by hitting a 2-point goal, a 3-point score by hitting a 3-point goal. And that's probably enough, because after that I can just add 2-point buckets to each of these. right? So the hard part of this, I guess, is stating it clearly. Note that 2 points can be scored with a 2-point goal. Also, note that 3 points can be scored with a 3-point goal. Duh. I started with 2 because that's the smallest one, right? I went 2 because I'm going to reach back, a couple points to get the rest of them. Okay? Thus, the initial step holds. Now, assume that we can score J points. J is anything up to K for some K, and K would have to be 3 or bigger. Okay, now why is that? Well, the next, if K is 3, then the next one up, the lowest thing K plus 1 could possibly be is 4. And how do I get 4? Well, I add 2 points to my 2-point goal, right? 5, add 2 points to my 3. 6, add 2 points to my 4, and on. Okay, but that's what I'm saying. It's our key here is that we're going to add a 2-point goal. So that's why we had to get the first 2, and that's why we're letting K be 3 or bigger. We always look at this last one, right? And we've got everything up through there. Then, based on this assumption, to score K plus 1 points, we score 2 less than this, K minus 1 points, which by our assumption we can do, and then add a 2-point goal. Thus, the inductive step holds. Therefore, by strong induction, the statement holds. Okay, not a hard one. That's not a hard one. All right. All right, I think in 14 there's a couple parts, and they have us using stamps. It's the same basic idea, but now we've got a variety of different stamps. So in 14A it says, all right, we can only use 3-cent and 10-cent stamps. Show that all amounts above a certain amount can be paid. And this is where you got to do a little playing around here. Let me. They don't tell us what the amount is, but let's get a little scratch paper over here to the side. And this is where you kind of look at things. You could have, 0, 3, 6, 9, 10 would be if I add a 10-cent stamp to the 0. And then I could get 12 here, 13 there, 15 here, 16 there. And what I'm looking for here I got to have 3 of these in a row, right? As soon as I can do that, as I get this one, this one, this one, then to get this one, I just have to add a 3-cent stamp to this one. Okay, so I'm looking for 3 in a row. I had 12 and 13, but no 14. I've got 15, 16, but no 17. I've got 18, 19, and 20. Right, if I had 2 10-cent stamps. 18, 19, 20 means I can get everything from 18 on. Once I get 18, 3-cent stamp. 19, 20, and so on and so on and so on. So let's say this right. The amount is 18 cents. And the way we prove that with strong induction now is note that we get 18 cents with 6 3-cent stamps. Also, we get 19 cents with 3 3-cent stamps and 1 10-cent stamp. Lastly, we get 20 cents with, 2 10-cent stamps. Thus, the initial step holds. Okay? So you see that we're set up and ready now, because the rest of it I can just get with 3-cent stamps. We just need to say it correctly. Now assume that we can get J cents postage, where J is between 18 and K. And we're going to do this for some K bigger than or equal to our last one, which is 20 cents. Okay? Consider K plus 1 cents postage. And all we got to say is, well, since I can, 3 cents less than this would be K minus 2. And let's see, if K was as small as possible, that'd be 20 minus 2 is 18, so we got that. Whatever it is, it's less than K, so we got it. Since we can, by assumption, get K plus 1 minus 3, which is K minus 2 cents postage, then just add a 3-cent stamp to the postage to get K plus 1 cents. Thus, the inductive step holds. Therefore, by strong induction, the statement holds. Okay? Box. All right. Those are not terribly hard proofs, but we are a little persnickety about, how we state things. Okay? So let's make sure we're stating things correctly. And then to wrap up the rest of this problem, it says, suppose only 4-cent and 10-cent stamps can be used. Prove that there are infinitely many postage amounts that cannot be paid. Well, this all goes to the fact that 4 cents, the proof here is a direct one, actually. 4 cents is an even amount, as is 10 cents. Thus, any multiple of any stamp is even, and any sum of the stamps would be even, since there are an infinite number of odd numbers. Positive odd numbers, doesn't really matter. The statement holds. C is very similar. It says suppose only 3 cent and 12-cent stamps can be used. All amounts over a certain amount, or an infinite number of postage amounts that cannot be paid. Well, it's the infinite number of postage amounts that cannot be paid, right? These are both, again, each of these is a multiple of 3. So any non-multiple of 3 cannot be postage. And there's an infinite number of those. Conjecture, what really has to happen here is that you have to, and we'll probably say more about this later, but the amounts need to be relatively prime, which means no common prime factors. The reason for that is if there is a common prime factor, then that would be the smallest. You get all your postages would be multiples of that smallest prime, and things that weren't multiples of that prime would not be postage. Okay, that's it. We got through the homework on that. I hope these integrity homework sessions are helpful to you, and I will see you in class on Tuesday.